Hi there, welcome to tutorial 11. So we have covered a lot, so now we're going to enter into the part where we are going to address the corrections to the eddy viscosity models. We studied that in the theory, and we're going to address two particular corrections. So it will be the production limiter and curvature correction. So in the first tutorial, we're going to talk about the production limiter. So let's talk about the case that we're going to see here. So as you look at the screen, so again, another validation case coming from the aeronautical industry. So this is a transonic flow over a RAE airfoil. So far we know how to create the geometry using the same modeler, space claim, generate this mesh, and so on. Okay, so I'm not going to address any particular about that. Also how to plot normalized velocities and so on. So what we're going to study is this particular deficiency that we're going to find the linear viscosity models, which is the overproduction of turbulent kinetic energy. We're going to see what we're talking about here after. So here we have a few references, okay? So you can visit these links or download these papers, are all available. So this is the geometry that we have, our airfoil. Now we have a C domain, C topology, okay? And this is our mesh, instructor mesh. So we have our inflation layer close to the airfoil, triangular mesh with a nice transition. The case is a wall modeling, by the way. Later we're going to see a little bit more about that. But then also remember that, and I want to stress this about airfoils, that you need, if you change the incoming flow, you need also to rotate the axis about you are computing the forces and coefficients. So here you have a recall and you have the rotation matrix. Okay, we also addressed that previously, but I like to address this one and to stress this because a lot of people forget to do this. Okay, and this is the results that we're going to get. So we're running this airfoil, this Mach number, and this angle, relative flow angle. So there is no massive separation, nothing like that. So we look at the contours of Mach number and see that we're in supersonic conditions. We have here the clear shock wave, and here the contour of pressure. See that you have also the change in pressure as indication of that fingerprint of shock wave. So we have it there. So this is a more severe physics. Dealing with shock waves is not easy, but Fluent is very robust that it's going to give it good solutions. Now we look at again at the viscosity ratio, that quantity I already mentioned that people don't look at that very often, and this is very important. Remember, just to check if you have a good mesh, okay, so you are not adding too much transition into your solution. And conversely to what we did previously, that there was transition modeling and we have verified meshes and it was very good meshes. Look at here, that is, you look at here in the rear part of the airfoil, see that we're getting that transition from the prismatic cells or rectangular cells to the triangular cells quite fast. Okay, and when I talk about adding numerical diffusion due to that transition, probably here you see. So this is very important to control. Okay, remember that we talk about that viscosity peaks in the middle of the boundary layer, kind of, you have it here. Okay, so probably you see that if you look at the airfoil in most of its extension, this mesh is okay, except here close to the trailing edge. That maybe it might be a good idea to add another transition layer or probably reduce the transition. Okay, but it's not that critical, it's not that bad. But this is what I was talking. See here that kind of you start to see that you are adding some diffusion there. That in some situations might be critical. Okay, and now we look at here, and this is what I want to arrive, the turbulent kinetic energy. Okay, so see that we have two solutions here. One with production limiter disabled and the other was the production limiter enabled. And see that the difference is large, okay? At least from the qualitative point of view, okay? And the idea of these production limiters is to attenuate the excessive generation of turbulent kinetic energy in stagnation points. And additionally, I might add that when you have shock wave also, it might also attenuate that production there, okay? Positive, or it might not be, okay? This needs to be assessed, but clearly one of the advantages here. So look at here in this stagnation point and see that this that looks like some diffusion, but in reality is excessive production of TKA, okay? And that might be a problem in some cases, and in particular when we deal with transition to turbulence, like in the previous tutorials. And probably as you go back to those tutorials, you will see that 2 production limiters were enabled. Okay, just to avoid that, because that can trigger artificial transition. Okay, so using this production limiter is critical in transition modeling. Using standard turbulence models is the user choice, but usually it's recommended to enable. By default, it is enabled, okay? So clearly we see this impact here that it might or it might not be, okay? It's not necessarily what you will find, but it might or it might not be. You might have that influence in your forces prediction and heat transfer rates, okay? Again, this is a validation case, so there is some data available. So see here that we compare with experimental data, the pressure coefficient, so quite good agreement. Then we have some differences here, but this is not to be worried about, okay? So whole software will have problems here. So also this depends on the mesh. So if you have a superfine mesh, you will capture better that shock wave. And here also we compare friction coefficient, okay? So we kind of have a trend, okay, what is important. And also we have information about the CD and CL, okay, experimental and numerical values. Okay, so see that we have a comparison here and we have a relative good agreement, okay? So, but remember also I want to stress that even if you have this experimental data, just be careful that this doesn't mean that this is the actual true data, okay? This data might be wrong, okay? You never know that how that experiment was done. And also there are some sources of uncertainty. Look at this angle 2.79, okay? Kind of how do you measure with that precision data in the experiment, or do you guarantee that you have that precise angle? But in any case, we have a very good agreement, okay? So this is the case that we're going to run. And as you go to the web page, okay, you will have access to the data here. So again, you can download the Fluent files, okay? The case is ready to go. And or if you want to set up everything from scratch, you have there the meshes and also the setup plus the additional validation data. So you're going to have these folders, okay? Fluent cases, meshes, super material, I think you have that one about validation data, but just to show you the Fluent cases here. So you're going to find 3 folders, 3 cases, okay? So you have density-based solvers and pressure-based solver. I'm not going to talk about the density-based, I'm going just to address the pressure-based solver, the one that I recommend you, but you have also the setup here, and then you can compare and draw your own conclusions. And then you have the same setup using the pressure-based solver, lowest speed, okay? So this is Mach, high Mach number, this is Mach, I know, 0.2, I think, just to show you that nothing changed. Still, you're going to have that overproduction of TK in the stagnation points, okay? Finally, just to show you here, you have a very nice link, this one here. Okay, so let me just show you that this is, they have a very extensive validation, okay, and comparison with some other solvers. Let me put it there. Okay, and this is the link, okay? So see here that if you go to any of these links, you will have different solvers, okay? And see here the comparison using some state-of-the-art solvers used by NASA. See that it's still, I just want to stress that still you have this different here for those that are worried that, well, but there is a problem, I have a problem. It's still very sophisticated software, people that knows very well what they are doing, okay? Have problems, okay? So see here that you have a very nice comparison, very different methods. So see that some specific solvers have a better agreement with the data, but some others are a little bit far, okay? So just compare that data there also, okay? And then you can draw your conclusions, you can compare your similar turbulence model. So with this, I will end this transition, okay? This introduction to this case. See you in the next video where we are going to work out in the case setup. Thank you very much for your attention. See you next time. Bye.